Hello, SWIG Earth Science students, and welcome to another recorded lecture. This is week 6, Plate Tectonics, which will be chapter 4 in your textbook. Again, please make sure you read your text. I will be presenting the information in a different order, in a different way than your textbook does. I happen to get really excited about plate tectonics. It's one of my favorite topics to talk about, so this one may be slightly long-winded, but it's a really cool concept and topic. So, we are going to be talking about Earth's interior in order to understand plate tectonics. So Earth's interior, it is layered. We talked about this a bit when we talked about the differences between the terrestrial planets and the Jovian planets. Earth, like all other planets, is layered. Our Earth has an inner core and an outer core, which are the same composition, but they're different phases. So the inner core is solid, the outer core is liquid. Then we have our mantle. The mantle is solid rock, but it is able to flow over geologic time. And above the mantle, we have the crust. There are different ways of looking at the layers. I will talk about that in a minute, but those are the basic layers. So the way we know this is due to seismic waves. I will talk about that as well. But basically, we can't get down into the interior parts of the Earth. We know the composition based on looking at bulk composition of the solar system through meteorites. We also know the composition based on looking at how seismic waves travel through the interior of the Earth. They travel at different velocities depending on what materials they're moving through. So Earth is layered. But there are two different ways to look at these layers. So we have the physical layers and we have the chemical layers. The layer boundaries are not always the same. In fact, in most cases, they are not. There's only one boundary that's the same in both naming structures, and that is the boundary between the bottom of the mantle and the outside of the outer core. So this boundary here between the orange and the yellow is the only boundary that's the same in both ways of looking at the layers. So I'm going to start off with the chemical layers because it's a little bit simpler. There are 3 chemical layers, and the chemical layers on this side. So we have, starting from the outside going in, we have the crust. The crust has a variable thickness because we have oceanic crust, which is very thin, and continental crust, which is a little bit thicker. So we can see that here. The oceanic crust is about 10 kilometers thick on average. The continental crust can be anywhere from as thin as 25 to as thick as 70, but 35 to 40 would be an average. The crust overall is extremely thin compared to the rest of the planet. Then we have the mantle. The mantle is by far the most voluminous layer of the planet. It is separated from the crust by the MOHO, which is an abbreviation for the Mohorovich discontinuity. This is where we go from crust to mantle. The mantle has layers as well. Most of those layers are physical layers. That has the same chemistry but has different properties. Again, it's the majority of the planet. It's about 2,900 kilometers thick. And then our final interior layer is the core. So the core we normally think of as being an outer core and an inner core, but if we're looking at it chemically, it's the same layer. It is iron and nickel. It's when we look at the physical layers or mechanical layers, that the core is separated into 2 layers. So the physical or mechanical layers are much more complicated. This is where we're looking at things based on their physical properties. So the outer layer, and if we're looking at this image, the physical is this side. So the outer layer is the lithosphere. Litho means rock, sphere means shell. It's the rock shell, the rigid plate that forms the outside of the planet. It is variable because the lithosphere includes the crust. So the crust is variable. We have that ocean versus continent, so the lithosphere therefore is also variable laterally. The lithosphere also contains the uppermost part of the mantle. It's the lithospheric mantle. And again, this is the solid shell that forms the plates. So the lithosphere is going to be, 100 kilometers thick or so. It varies again depending on ocean versus continent, but it's still the thinnest layer of the physical layers. Below the lithosphere, we have what's called the asthenosphere. This is all in the mantle. It is the weak part of the mantle, and it can, quote, flow over geologic time. So this is the part that allows the plate tectonics to happen, to have the plates actually moving. So the boundary between the lithosphere and the asthenosphere is called the lithosphere-asthenosphere boundary, or the LAB, whereas the MOHO is the boundary between the crust and the mantle. So those are two different boundaries. They're in two different locations. So we see the MOHO here is going to be much shallower than the lithosphere-asthenosphere boundary. Below the asthenosphere is the mesosphere. Meso means middle. It is the lower mantle. This is the part where the mantle regains its strength. The mesosphere can still have convection occurring. We will talk about convection in a minute, but that's what allows the asthenosphere to flow. But it is much stronger than the asthenosphere. And then we move from the mantle into the core. So we move into the outer core. Again, this boundary, moving from the mesosphere to the outer core, or the mantle to the core, is the only boundary that is consistent between the two structures or systems. The outer core is liquid. It is what contributes to our magnetic field. It's about 2,200 kilometers thick. It is iron and nickel. And then we have the inner core, which is solid. It is also iron and nickel. The two cores together are what makes our magnetic field, particularly the outer liquid core. If we don't have a liquid layer in the planet, we're not going to have a magnetic field. The inner core is about 1,200 kilometers thick. So this is the densest part of the planet. So as we move through the Earth, we see properties change. So this graph is looking at temperature. Temperature increases as we go with depth in the planet. It increases fastest in the shallow layers. So if we look at how quickly we go up in temperature versus down in depth, we see here in the shallow layers in the crust, we increase temperature very quickly. It's about 30 degrees per kilometer. So it's a very fast increase. That is called the geotherm. Actually, this entire line is called the geotherm, but that's the continental geotherm. Once we get into the mantle, that we still increase temperature, but it's much more gradual. As we approach the mantle core boundary, we increase in temperature a little bit faster, and then we gradually increase in temperature again as we go through the rest of the core. So it's very hot in the center of the Earth, but the temperature increase per kilometer of depth is fastest at those boundaries, particularly in the crust. We can also look at how density changes. So this chart, which I have on its side so that it's showing a similar, that we're going from shallow to deep, is showing us how density increases. So we're increasing density going this way with depth. So our density is going to keep going up as we go through the different layers of the Earth. These drastic jumps are going to happen at boundaries. So for example, when we go from the mantle to the core, we see a huge jump in density. When we go from the liquid outer core to the solid inner core, we see another jump in density. So we're going to keep increasing density as we go to different materials and different layers. So how do we know these things? Oh, sorry, that's not where I want to go. Now I'm going to go through the different layers and talk about them all a little bit. So we're going to start in the interior. And the interior of the core is about 16% of the volume of the Earth. It's iron and nickel. We have a liquid outer core and a solid inner core. The solid inner core was discovered by Inge Lehmann in 1936. That's this lady here. 1936, we had the tools to do this, but I work with these tools personally, and I am flabbergasted at her ability to discover this with the technology of the time. So the way that we she was able to discover this is using seismology. So I am a seismologist. I study earthquakes as well. What she observed is called a shadow zone. So these are images showing the energy of earthquakes moving through the earth. And so we have an earthquake and it will radiate out energy in all directions, and it will move through the interior of the earth as well. And how it moves through the earth will depend on what it's encountering. There are certain waves, certain types of energy that can't move through certain types of materials. So, for example, if we look on this side, the liquid outer core, certain waves cannot move through liquids, and all waves will be bent. They will alter their path when they try to enter a liquid. And Inge Lehmann was able to observe this happening. It's called a shadow zone, where we're not observing any of that energy because it's being redirected by the liquid. She was able to observe these around the world for different earthquakes and determine that there had to be a inner layer, or an inner solid layer within that liquid outer core, and she was able to determine the size of it as well, based on the relationships between earthquake location and arrivals around the world, which is extremely impressive in 1936 when she was looking at analog seismic instruments, and she was only able to do this with the largest earthquakes because the instruments were not terribly sensitive. So again, she observed these areas where there was a lack of seismic energy arriving and knew it had to be because they encountered different layers within the earth. And she was able to determine, based on where she did see arrivals, that there had to be a solid inner core, which allowed certain arrivals to go through as well, and it altered their trajectory by moving through this combination of liquid with solid inside it. Pretty amazing for 1936. The mantle is the largest by volume. It's 82% of the Earth's volume. So it's thick, but it's also further out in the planet. So it's thick, and it's also it's not just the nugget in the middle. The rock type is called peridotite. It's an ultramafic rock. We will talk about rocks next week, I believe. So this means it has a lot of iron and magnesium, and other heavy minerals. This is the stuff that, is quite dense. So basically our density gets less as we move out from the interior of the earth. The mantle is really dense. It's not as dense as solid iron and nickel, but it's still quite dense. The mantle is solid, but parts of the mantle can flow over geologic time. And remember, geologic time is that extremely long amount of time. We're talking deep time. Over that long period of time, we can have this rock flowing. So an analogy for this would be silly putty. If you look at silly putty, it's solid. But if you roll silly putty into a ball and set it on a desk and you come back an hour later, it will have kind of spread out into a puddle because it can flow under long periods of time. If you take that silly putty and pull it apart very fast, it will break in two. It will break. If you pull it apart slowly, it will stretch and bend. That's what the rocks in the mantle can do, only we're talking a much, much longer time period than what we would see with silly putty. So the way the rocks move within the mantle is through this process of convection. We will come back to convection multiple times. It's also important when we talk about weather. So convection is a transfer of heat by moving particles. So for example, boiling water. Hot water rises to the surface. It will displace the cooler water that was at the surface that then gets pushed towards the bottom where the heat is. And so we will move heat through the boiling pot of water. Another way to think about this is a lava lamp. A lava lamp has a light bulb in the base. That is the heat source. There are two different fluids inside the lamp. One has a property that as it heats, its density reduces. And so when you heat it up, it becomes less dense and it will then float. As it floats up away from the heat source, it will start to cool down. then it will drop because its density will increase again, and then as it drops it will approach the heat source again where it heats up, and then it will basically have this cycle. This it's a cycle. There's a term for that, and I can't remember what the term for this is. But it will have this pattern that it will follow this cycle. Cell. It's a cell. It's a cell where we talk about these as being individual cells. The same thing happens in the mantle. That basically hot material will rise up. It cools off as it gets away from the hotter temperatures of the interior of the Earth. As it cools down, its density increases, and it will start this process over again. Cycle. It's a cycle. The final layer is Earth's crust. So Earth's crust is the most variable layer. This is all the stuff that doesn't fit somewhere else. So we have two different types of crust. We have oceanic crust, which is a rock type called basalt. That's this rock type here. It is slightly denser than the continental crust, which tends to be thought of as granitic, which is this rock type. So because the oceanic crust is slightly denser, it's made up of denser materials. It's more of that iron and magnesium, the heavier materials. It will sit slightly lower than the continental crust, and that's why water collects there, because it's the low-lying areas. So that's why our oceans are where our oceans are. So this chart here is showing us the elements that are the majority of the crustal composition. Oxygen and silicon are in most of the minerals that we see. That they are the quote silicates, and then we see these others in combination with it. On this bottom part, we see different rock types with increasing densities. We can think of the continental crust as being granite. We can think of the oceanic crust as being basalt. And gabbro. Gabbro would be the lower parts of the oceanic crust. Peridotite would be what our mantle is made out of, and then this is a image of a meteorite that's an iron nickel meteorite, and that's what our core looks like. So basically we are looking at the layers as we go into the interior of the Earth. Another way of looking at the chemical composition here would be breaking up our crustal composition into the 8 elements that make up 98.5% of the crust. Again, primarily silicon and oxygen. They are going to be in most of the crust forming minerals. Sorry about that. I see a note in my notes that there was a typo, and I have fixed the typo. The typo is fixed the aluminum on this chart. You can see this is a different text. There was a typo there, but I have fixed it. So these 8 elements make up 98% of the crust. Again, oxygen and silicon are found in most of the crustal forming minerals. They're called silicates, and then we have different combinations of other elements with them. So elements like iron, magnesium, aluminum, potassium, sodium, calcium, etc. These are going to combine in different ways. So we do see that, for example, silicon is lower by volume than its weight or its number of atoms. Oxygen's higher by volume. That has to do with their atomic numbers, basically. How much space do they take up, or do they have more atoms and things? So there are 2 types of crust. We have continental crust, which is thicker and less dense. It's made up of more of like the granitic materials, and then we have oceanic crust. It's thinner and more dense. So what ends up happening is that the oceanic crust, because it is more dense, will sit a little bit lower than the continental crust, and that's why we have oceans there because that's the low-lying areas where the water will collect. The crust is 0.1% of the Earth's volume. It is separated from the mantle by the MOHO, again, the Mohorovich discontinuity. And again, we have these two different types of crust. That we have a very variable continental crust. It can be anywhere from thinned out in areas like the Basin and Range, where it's like 20 to 25 kilometers thick, to 70 to 90 kilometers thick in thick mountain ranges like the Himalayas. Its density varies a little bit as well. Basically, anything that doesn't fit as a specific composition in one of the other layers will go into the crust, particularly into the continental crust. The oceanic crust is much more consistent. It is between 5 to 10 kilometers thick. The differences in thickness will depend on its age. The older it is, the thicker it is. The oceanic crust we're going to learn can only get to a certain thickness though. Its density is much more consistent, again, because it tends to be basalt. It's one rock type. It's not nearly as variable. It has a lot of magnesium and iron in it. So the oceans and the continents are quite different. The composition is going to be different, which is going to lead to all the other differences. So the oceanic crust is made out of basalt. It's denser. It sits lower than the continental crust. The continental crust is much more felsic, which is another term for granitic. It is less dense, so it will sit higher. The oceanic crust is much thinner. The continental crust is much thicker. This also has to do with the density, that they balance each other out. And the final major difference is their age. The continental crust is much older. It doesn't subduct, which we're going to learn about today. It doesn't get destroyed, whereas the oceanic crust is constantly being recycled. It is very young in general. The oldest oceanic crust is only about 200 million years old, which we learned last week is very young for the Earth. So today we are talking about plate tectonics. What is tectonics? Tectonics is large-scale geologic processes that deform the Earth's lithosphere, producing landforms such as ocean basins, continents, and mountains. So we break the crust, not the crust, it's the crust plus the upper mantle. We break the outer shell, the lithosphere, into tectonic plates, also called lithospheric plates. These will move thanks to the underlying weak asthenosphere. So they move in a very choreographed dance around the outside of the planet. We can define the shapes or the boundaries of these plates by earthquake and volcano locations. So here we see the plates themselves. This lower figure is showing us in blue dots the locations of earthquakes, in red triangles the locations of volcanoes, and we can see that we outline these earthquake locations these plates very well. We can also see some of these boundaries even in things like Google Earth. So I have pulled up Google Earth here. This is actually these cracks that we can see going through the middle of the Atlantic Ocean are actually the boundary of our tectonic plates, and we can see another boundary here. So we can actually see these through images in things like Google Earth. All right. So before we actually get into plate tectonics, I always like to tell the history of plate tectonics, where it came to be, because this is a cautionary tale in science. It's a very interesting tale. So before we had plate tectonics, we had a thing called continental drift. Alfred Wegener was a meteorologist, actually, who made some very astute observations about the planet in 1915. Actually, he made these over the course of several years, but he tried to make his point to the scientific community over the course of several years. The next slide will say 1912. Wegener observed he had 5 lines of evidence that he observed, and he came up with this idea that would explain his lines of evidence. So he came up with a hypothesis, but his problem was he couldn't figure out a mechanism that would explain his hypothesis. So he had these 5 lines of evidence. He saw that the continents fit like puzzle pieces, that he found fossils on different, the same fossils on different continents. He found plant fossils in glaciated areas that indicated tropical environments. He saw the same rocks on different continents. And then finally, he saw glacial deposits in tropical and desert areas. So these 5 things, the only thing he could think that would make sense to explain all 5 of these lines of evidence is that the continents moved and that they, were not always in their current locations, and they used to all be together in what he called Pangea, into one major landmass. So when asked how he thought they had moved around, he didn't have a good mechanism. He basically, the only thing he could come up with was this idea that the continents plowed through the oceans like a boat. The problem is, if the continents had moved through the ocean at crust like boats, we would see evidence of that. We would be able to see, much like a boat going through water, we would see the path behind the continents, and we don't observe that. We don't see a wake. So his idea was ultimately rejected. So in 1912, he proposed continental drift hypothesis to account for these 5 observations. This is an image of Wegener in Greenland, actually, on one of his expeditions. So he looked at the continents and saw that they seemed to fit together, particularly when we look at, say, Africa and South America, that they just seem to fit perfectly together. He also saw evidence of past glaciers in areas that are now tropical. So here we see glacial polishing. He saw extent of glaciers in places like India, Africa. These are places that don't, unless they're high mountaintops, don't have glaciers today. So we see Permian glacial deposits and striations in regions where we don't actually have glaciers today. They're impossible to explain without moving the continents. And the only way we get glaciers in these regions is if they're at the top of a mountain, and these glaciations are not being seen at the top of mountains. So this is his idea of Pangea, that we pull all the continents together, and the parts where we see the glaciation, we're sitting at a more severe latitude than they currently are. So this would have been the southern polar ice cap at the time of the Permian. He also looked at climatic belts. So he saw that deserts of the past, or equatorial areas of the past, would have been in different regions. So he sees evidence of tropical life in places like Antarctica. He sees evidence of glaciation at places like the pole. So this is closely related to the previous one. So these are basically, we're seeing evidence of tropical regions that are not in the tropics anymore. We're seeing evidence of glacial regions that are not in polar regions anymore. So ultimately, what we see is that late Paleozoic rocks preserve evidence of these ancient climate belts. The belts align in a sensible manner, like the climate belts of Earth today, when we put the continents back together into a single supercontinent. He looked at fossils and saw the same fossils across ocean basins. So this may be possible for things like an aquatic species, but how do land species make it across an ocean basin? How do plants make it across an ocean basin? And in particular, some of these plants and animals were seen on multiple continents, including Antarctica. So Mesozoic fossil organisms occur on many of these southern continents, but these creatures would not have been able to migrate across an ocean. Again, bringing the continents together explains the occurrence of these organisms on different continents. He also saw rock units across continents. So It may be possible for a living organism to make it across a body of water, but how does a rock make it across a body of water? So we see distinctive belts of rock occurring on both South America and Africa, and they match up when present day Atlantic Ocean is removed from the equation. Um, we also see Paleozoic mountain belts on either side of the Atlantic Ocean that match up. So we are seeing these same geologic units across ocean basins, which also helps because the continents fit together, as we see here. Again, South America and Africa seem to fit together. We see this, it's not just South America and Africa, we see this across the entire globe. So Wegener saw these things and thought that the only way to explain them is that the continents used to be together. The continents were not always in their present location. In the past, they were all part of a supercontinent that he called Pangea. Pan, all, Gea, Earth. So he felt they had to once fit together, and then later they drifted apart, which is why he calls it continental drift. So why did Wegener fail? In the end, his hypothesis was abandoned. So there were two main reasons. The main reason that we like to say is that it lacked a mechanism for moving those continents. We did not, we didn't have a way to explain how the continents could have moved, which is true. But there's also an issue, a part of the story that is the cautionary tale, is that Wegener was not a geologist. He was a meteorologist, and so his ideas were discounted partly because he was not seen as being someone who, was an expert, who had a place in the field. It's a rather sad story. Wegener ends up dying in Greenland on an expedition before he becomes vindicated. His ideas are not ever accepted during his lifetime. So it's unfortunate. So continental drift was rejected. But that's not the end of the story. So as the years progress, we start collecting new data and we start seeing new evidence, particularly looking at the magnetic signature of rocks. So we see two things, polar wander, which I will explain, and seafloor magnetic reversals. These are both going to be based on Earth's magnetic field, so I need to talk a little bit about magnetic fields before we talk about the evidence we see. So Earth has a magnetic field. This is because of our liquid outer core. You can think about it as a giant bar magnet. So the current magnetic field has a southern polarity in the north, which is why our compass needles point to the north. The magnetic field of a bar magnet has invisible lines of flux. Basically, we have magnetic field lines will come out of the South Pole and move into the North Pole. And this is why your compass needle will point in different directions depending on where you are. This also, the reason your compass will change directions is because it's iron. It reacts to a magnetic field. Rocks also can have ions in them and can react to magnetic fields. There are two aspects to the magnetic field. We have one that's called inclination. Inclination is how steep those lines are. So we will see that at the equator, a field line would be parallel to the Earth's surface. At the magnetic pole, it's going to be perpendicular. So basically, the compass needle will dip down based on what latitude you're at to match these magnetic field lines. The other aspect of the magnetic field is the declination, which is basically where we are pointing to the pole. So that's going to change based on your longitude. So that's how it actually points to the magnetic pole. So paleomagnetism is this idea that rocks that have iron in them will also want to align with that magnetic field. So when rocks are extremely hot, they're not going to have a magnetization. As they cool down, the iron will want to align with the current magnetic field, and then as the rocks completely cool, the iron will be frozen, pointing at the magnetic field at the time that the rocks formed. So iron minerals and rocks will achieve magnetic field at the time of formation. In hot fluid magma, the iron magnetic particles are randomly oriented. As the magma cools, the iron-bearing minerals will become aligned with the magnetic field at the time of formation, and that signature then gets frozen in the rock. If we look at rocks from different time periods, they appear to point to different. Sorry about that, Heidi's barking. If we look at rocks from different time periods in a sequence, they appear to point to different magnetic poles. So if we're looking at rocks of progressively greater age, they appear to point to a different direction. So we call this polar wonder, or rather apparent polar wonder. So the different locations they're pointing to makes it look like the pole is moving around. But as a dipole, we can only have one north pole and one south pole at any given time on our planet. If we look at rocks from different locations that are the same age, they appear to point to a different set of magnetic poles. So here, if we look at the European rock and the North American rock, they at the same time period, so each of these is representing, each dot is representing a time period, appear to point to different locations. However, if we look at this path, the path is the same shape. So if we make the assumption that at every time period we only have one magnetic north pole and all rocks have to point to that north pole, we can then say that it's not the pole that's moving, it's the rocks that have moved. And that's why we call this apparent polar wonder. That because the rocks have moved, it appears that the pole is moving and we see a different wander path on different continents because the continents have moved independently of each other. There is a slight aspect of true polar wonder. The pole does move slightly over time, but it stays pretty consistently near the North Pole and the South Pole. So another important aspect of our studies is going to be looking at the magnetic signature of the seafloor. So if we move forward to after World War II, we got very interested in looking at the ocean floor during World War II because of the increased use of submarines. And so it was important to understand the ocean floors, and there was a massive push to study the science of the ocean floors. If we look forward to the 1960s, there's a man named Harry Hess who observed an interesting pattern in the ocean floors and proposed an idea called seafloor spreading. So he observed that there is this pattern of positive and negative polarity in the ocean floors that is symmetrical about centralized ridges that he called mid-ocean ridges. So his idea is that this is actually where we're creating new seafloor at these ridges, and it's pushing out the old seafloors. And as we create new seafloor, it's being magnetized in the current field. And one of the properties of a magnetic field is that it periodically reverses itself, or at least a planetary magnetic field will periodically reverse itself. And so this positive and negative polarity he observed is actually documenting these periods of positive, meaning current magnetic field orientation, and negative or reversed magnetic field orientation. So looking at the ocean floor, he sees this pattern of current magnetic field surrounded by opposite magnetic field with current then opposite, and it's the same pattern on either side of these centralized ridges. So we are having new magnetic floor being produced at the centralized ridge. It will be in the current polar magnetic field, and it is pushing out the ocean crust from that centralized ridge, and we see a pattern that records those polar field reversals that is the exact same pattern on either side of the centralized ridge. So this is what we're seeing with these polar reversals. Because Earth is a dipole, it acts as a bar magnet, and it's this field is generated by the liquid outer core, and it reverses periodically, that the North Pole becomes the South Pole and the South Pole becomes the North Pole. And we can actually create what's called a magnetic time scale off of this. We can see these patterns of reversals. So when we run a magnetometer across the ocean floor, we see this pattern. Normal and reverse polarity are symmetrical around these ridges. And Harry Hess put this together as this idea of we're producing new ocean floor at the centralized ridge. It is going to be magnetized in the current or in the magnetic field of the time it's being produced, and it will freeze that magnetic field. And this process will keep going. As the poles reverse periodically, which it averages out to maybe once a million years or so. I think it's a million years. It varies. There are periods of long and short. As it reverses, we're continuously making this new ocean floor. So we're going to see the ocean floor being magnetized in whatever the current field is, and then it will be frozen in. And so we're continuously pushing out, generating new ocean floor, and so we're going to have the same pattern on either side of this ridge, and it's going to work its way across the entire ocean basin until it encounters something. So here is a actual graphic showing this. So we see the magnetic polarity down here. We are producing our ocean floor up here, and we see this pattern moving across our ocean floors. I'll let that run for another 1 or 2 times just so you can kind of get an idea of it. So this ultimately is why we know, or why our ocean floor is quite young. We are continuously producing new ocean floor. So new ocean crust is being produced at our ridges. So if we look at the age of the ocean floor, the red is going to be the youngest, and that is where our ridges are, and our ocean floor gets progressively older out from there. The oldest ocean floor is only about 200 million years old. So the ocean is very, very young. That means something has to happen to the ocean, and I'll talk more about that later. But spoiler, the ocean crust will be consumed at some point, and we will talk about that later. But overall, the ocean floor is extremely young. So these boundaries of where we see ocean floor being generated and consumed is going to be outlined by earthquake locations. We have very small earthquakes outlining where the ocean floor is being created. We have very big earthquakes outlining where the ocean floor is being consumed. So when we start to put together this idea of continental drift, now we have this magnetic striping of the ocean floors, Harry Hess's seafloor spreading. We also have that polar wonder that we know the rocks have moved, and we take into account the locations of earthquakes and volcanoes. All of these together come back and help us explain Wegener's observations that the continents have moved. So Wegener was completely right. The continents have moved. They have moved a lot. What he didn't know was that it's not just the continents moving, it's the entire plate. So Harry Hess's seafloor spreading is the key to explaining Wegener's continental drift. That it's not just the continents moving, it's the continent plus the plate around it that's moving. So the seafloor is also moving. That's why we don't see wakes of the continents behind. The continents are just kind of going along for the ride as the seafloor is spreading. So Earth is broken into tectonic plates. Plates will interact either by coming together in what's called a convergent boundary, by pulling apart in a divergent boundary, or they slide past each other in a transform boundary. So the dashed lines are where they're coming together. The solid thick lines are where they are moving apart, and the thin solid lines are where they're just sliding past each other. So the plates are going to be made up of the crust and the rigid uppermost mantle. Um, the asthenosphere below is soft, and that's what's allowing them to move on top of them. So plate tectonics is this idea of these plates move, and they will come together and move apart, and come together and move apart. I previewed the Wilson cycle last week or the week before. That's what this is, this cycle of coming together into few massive landforms and breaking apart into many smaller landforms. And they do this as entire plates. So now I'm going to show you a reconstruction is what these are called. This is a plate reconstruction that is showing us for the past 400 million years or so how the plates have moved. So we are looking basically through the Phanerozoic, not quite the entire Phanerozoic. So we will start to see all of the plates coming together very soon here into Pangea. Remember, Pangea is going to come apart or come together during the Mesozoic and then break apart at the end of the Mesozoic. There have been several supercontinents throughout Earth's history. They have different names. There have been also periods of time when we don't have an entire one supercontinent. We have several larger continental masses, and those have names as well. But Pangea is the most famous of the supercontinents. So here we can see that everything had come together. Now it's starting to break apart, and we're starting to see like the Atlantic Ocean is opening up. I always am fascinated by India here. It is moving up at a very fast clip, and will eventually, this oceanic area will be completely consumed, and then India will crash into Asia. Honestly, India is still crashing into Asia. I'll show that again one more time. There are many plate reconstruction videos out there. This is one that's fairly quick, which is why I like to show it. It's rather fascinating the way that these plate reconstructions are put together. And the different symbols are representing different types of boundaries. I'm not going to go into all the detail about that. So we can see this is, Pangea at this point. And then Pangea will start to break apart. And again, we can watch the trip that India takes up into Asia, which will produce the most impressive mountain range we have on Earth today, the Himalayas, which are still rising, by the way. So how does all this work together? All right, so this works together in plate tectonics, which is a very elegant concept. It explains so much of our planet. So we have seafloor spreading at our mid-ocean ridges, but we're creating new ocean plate, so we have to do something with the old ocean plate, and that is it's going to be consumed at subduction zones. We have a spherical planet, so we have to have these plates working together. That's what's going to happen at transform boundaries, where the plates just slide past each other. And the way this all works is convection. So we are going to have these cells, these cycles within the mantle that allows the plate to move across the surface of the asthenosphere. So there are different types of what are called plate margins. A margin is where two plates come together. Excuse me. So we have convergent or destructive plate boundaries. Convergent means they converge, they come together. Destructive means that material is destroyed there. This happens at subduction zones. So we can have ocean-ocean subduction, ocean-continent subduction, or continental collision. I will talk about all those in a second. We can have divergent or constructive boundaries. I know they're both a C and a D. Unfortunately, they're not the same one. So you really need to think about what the words mean. So divergent means to diverge or to pull apart. This is where we are constructing or creating material. So this happens at mid-ocean ridges or continental rifts if it's on the land surface. And the final one is a transform boundary, which are also called conservative boundaries. Transform boundaries are where the plates are just sliding past each other. It's called conservative because we're not creating, we're not destroying material. These are necessary to allow our planet to remain spherical. And then we also have what's called a passive margin. A passive margin isn't actually a plate boundary. What a passive margin is it's the edge of a continent that doesn't coincide with a plate boundary, so we don't have any movement happening. So for example, the eastern coast of the United States is the edge of a continent, but that's not the edge of the plate. The edge of the plate is in the middle of the Atlantic Ocean, so we call that a passive margin. So again, we can see these things in what's called bathymetry, which is the elevation of the ocean floor. So if we look at the mid-Atlantic ridge, this is going to be a divergent boundary with these individual lines will be small transform boundaries. The eastern coast of the U.S. is going to be a passive margin. The western coast of the U.S., part of it will be a subduction zone. So up here near Washington, this is a subduction zone. Parts of California are going to be a transform boundary, San Andreas Fault, for example. Where we see these deeper, darker bits, these are subduction zones. So the western coast of South America is one long subduction zone, and that's why we have massive earthquakes there. The East Pacific Rise is a ridge that is in the East Pacific. So we are creating oceanic plate here, and it's being consumed over here. So again, I will talk about all these things individually. So our three types of plate boundaries. We're going to start with convergent because it's complex, I guess. I don't know why I like to start with convergent. I like to start with convergent. So convergent is where the plates are moving towards each other. So they can move towards each other in different ways. We can have, the simplest one is ocean-ocean. So that's where we have two oceanic plates are coming together. One of them will have to go beneath the other one because if two things come together, something has to happen. Which one will go beneath the other one is going to depend on the relative ages. The older one will subduct. So the process that happens here is called subduction. Subduction is where one plate goes beneath another. We can also have ocean continent. The ocean is always going to subduct beneath the continent. It's just more dense. It's always going to want to go down. And then we can have continental collision or continent-continent. This is going to happen when we run out of ocean and two continents come together. So, convergent boundaries are destructive boundaries. We are removing material. So the ocean floor is being eaten through subduction because the Earth is not getting any bigger. The oldest ocean floor is typically 180 to 200 million years old. And again, the ocean floor that goes down is going to be the older ocean floor. So we can have ocean-ocean, ocean-continent, or continent-continent. The ocean will always lose because it's more dense. Whichever material is more dense is the material that will subduct. So the downgoing plate the subducting plate will go beneath the other overriding plate. We will have a line of volcanoes that will be formed from material coming off this subducting plate. In the case of ocean-ocean, we will have a line of volcanic islands. In the case of ocean-continent, we will have a line of volcanoes on the continent. The chemistry of those volcanoes will vary depending on what the material it's moving through is, and their size as well. So an example of this would be Japan, for example. So we have the Pacific plate is subducting beneath the Asian plate, I believe this is. And so Japan is actually a chain of volcanic islands that is being produced from this subduction. So this is what we actually see happening, that plate, the oceanic plate is actually going to go down into the mantle and break up, and we will see earthquakes all along here. This is where we're actually going to get our largest earthquakes in these type of situations. So in ocean, the subduction of one plate will produce melting, and that leads to island arcs of volcanoes. These earthquakes and volcanoes earthquakes outline the downgoing plate in what's called a Benioff Wadati or Wadati Benioff. It's listed both ways. So this is mapping the location of the earthquakes, and this is actually outlining this downgoing oceanic plate. This happens in Japan. Another good example of this is the Aleutian Islands in Alaska. So the leg that kicks out is formed due to oceanic plate going beneath other oceanic plate. So these are all volcanic islands. Ocean continent is basically the same idea. The ocean is always going to lose. It's more dense, so it's going to go down. So instead of having an island arc, we now have a chain of volcanic mountains. So they will be more complex chemistry. They will be higher. So an example of this would be the Andes in South America. And so these are going to be very active volcanoes. Again, this is also where we're going to get some of our largest earthquakes. So the two largest recorded earthquakes in history happened in Chile and Alaska in this type of a situation. And then the final type of convergent boundary would be a collisional boundary. So this is where we have consumed all of the ocean plate that now is going to be pulling along a continent from behind it, and then we're going to lead to crashing collision. So basically we had an oceanic plate being subducted, and then we have eaten all of that oceanic plate, and it's pulling along the continent behind it, and eventually that continent is going to keep coming, and it's going to collide into the other continent. So the one doing the colliding is going to be the one that was being consumed. So who loses in this case? This is going to occur when the plate that had both ocean and continent is being subducted, and all of that oceanic crust has been consumed. Ultimately, it will stop, but it takes a long time. India, that says India, not India. India is still moving into Asia. So eventually it will stop, but it does take a long, long time to stop. And I fixed my typo now. Next type of boundary, divergent boundary. This is where plates move away from each other. So it's a little bit simpler. So there are two ways the plates can move away from each other. We can either have it happening on continent or in the ocean. If it happens on the continent, it is called a rift. So the East African Rift is an active rift. The Red Sea started as a rift and evolved into a mid-ocean ridge. Eventually, the East African Rift will break off East Africa from the rest of Africa, and we will have ocean floor being produced here, much like what we are currently seeing in the Red Sea. So rifting is where we are going to break apart continent and be producing new crust. The new crust we produce will be oceanic crust, so it will sit at a lower elevation, and eventually water will collect there and we will form a new ocean. We can also have these happening in the middle of an ocean. This is called the mid-ocean ridge. These are the more common ones. So this is where we are producing that new oceanic plate, and it's going to be hot and young at the ridge. As it moves away from the ridge, it will get older, and it will actually start to get thicker and a little bit denser, and so it will start to sink, and that's why older oceanic plate is always consumed, because it's thicker, denser, and more likely to sink. So here we have age of the seafloor. The reds, again, are the youngest. The blues are the oldest. We see our oldest seafloor occurs on either these passive margins or right before it's being consumed. There's some pretty old seafloor kind of caught up here that just hasn't been consumed yet because it's kind of been pulled away from any sort of a subduction zone. But we don't have very old oceanic plate. Our oldest oceanic plate is only 200 280 million years old. So again, we know about this because of that seafloor spreading proposed by Harry Hess. So how fast the seafloor spreads, each plate is going to move at half of the rate that the seafloor is spreading because they're moving apart from each other. And we record this in our polar reversals and that pattern we see on either side of the mid-ocean ridges. So we are seeing new ocean floor being created, and it's recording a history of the magnetic field. And our third type of boundary is a transform boundary. So transform boundary is where the plates slide past each other. These are necessary because the Earth is spherical, and in order for the Earth to remain spherical, we have to have these transform boundaries. So if we look at a mid-ocean ridge, we actually see that it's not going to be continuous. So if we look at this mid-ocean ridge, the mid-Atlantic ridge, if we zoom in, we see that it's not a continuous line, that it's this zigzag. The zigzag pattern is the transform boundaries. So that is necessary in order to make the planet remain spherical. And so we see these small offsets that are transform faults. And then, we basically have one large plate that is this almost zipper separating it from another large plate. We can also have transform plate boundaries that are larger, and things like the San Andreas, where we have a large section where we have plates moving past each other. So we have these smaller transform boundaries between each of these segments of ridges, and then we can have a larger transform boundary. So basically, when we're moving from one set of ridges to another set of ridges, we will have a transform boundary. We see the same thing in subduction zones, just not as strongly as we see it in the divergent boundaries. Again, this is necessary to keep the planet spherical. So all of these small offsets are transform boundaries. So the plates are sliding past each other, sometimes at ridges, sometimes not at ridges. This is a little bit more than I really need you to know, but again, this is kind of my jam. So there are different ways to look at how this ridge transform thing could work. One idea would be that the ridge used to be one continuous ridge and then it's been offset by later faults. Evidence doesn't support that. Evidence supports that the ridges are independent and these faults connect the ridges. So we have one big plate on one side and another big plate on the other side. So again, this is a little bit more than I would expect you to know. I just like to talk about it to show that yes, these are a set of faults that work together. So how does all this come together? It comes together through things called poles of rotation. The Earth is a sphere, so we will rotate about what's called an Euler pole or a pole of rotation. So if we say that the pole of rotation, it doesn't have to be, but for this example, we're going to say it's at the North Pole, and we can move objects about that one, or about, basically we rotate about that central location. As our plates are splitting apart, they're going to be splitting apart around a pole. The closer they are to the pole, the less movement they have. The further away, the more they break apart, which also explains these offsets, our transform boundaries. So for example, when we look down here at plates A and B that are splitting apart around this pole that happens to be at the North Pole, we see greater offset the further we get away from that pole, and then it decreases as we go the other way. So that's what this is showing here, that our gap gets bigger as we move further away from that pole. So the transforms will be along small circles, and our ridges are along great circles when we think about them in reference to that pole of rotation. And the spreading is going to decrease as we get closer to the pole. Convergent plates also do this, but again, it's not quite as obvious as it is in the divergent plates. When we have three of these boundaries, or three plates coming together rather, they come together in what's called a triple junction, because there are three of them. There's 16 different combinations that can happen. Not all of them are stable. So when the relative velocities of the three plates coming together is balanced, it's stable. So this can happen, for example, if we have three ridges, that will be stable. They will be balanced. We can't have three trenches. That won't be balanced. I'm sorry, it will be balanced. If you have three transforms, that is unstable. It's not balanced. So only certain ones of these will be stable. We can actually use these triple junctions to determine the velocity of plates and the type of margin, so what type of boundary it is, and where they're going. It doesn't always tell us where it's going. It'll only tell us where they're going for certain ones. It doesn't tell us which plate is going to subduct. We just know that they're coming together, so which direction they're coming together. This is important because we can use it to determine past plates. So for example, we know there used to be a plate called the Juan de Fuca. I'm sorry, there is a small plate called the Juan de Fuca. It is off the coast of Seattle and Pacific Northwest. There used to be a plate called the Farallon plate that was connected to the Juan de Fuca plate. And so by backtracking the location of triple junctions, we determined that the Juan de Fuca plate is a small remnant plate still there. Most of the Farallon plate is actually underneath the United States. So we can use these to find extinct plates. And so this is how we do this plate reconstruction that I showed you the video of. So the ways we do that is we look at removing the ocean floor and backing out where those ridges have been, or I'm sorry, those triple junctions have been. We can also look at paleomagnetism. So we can look at how the pole has moved. So we can see how the rocks had to move by looking at their paleopoles. And then we can also look at geology. So we can basically try to piece, for at least the most recent locations, we can piece the rocks back together. And all this comes together to show us how we can form Pangea starting in the Mid-Ordovician, and then have it breaking up at the end of the Cretaceous. So we can start to see how it formed and then broke up. So the way that the plates are going to move, it's all going to happen in this thing called the Wilson cycle. So the Wilson cycle is this idea of plates coming together into fewer, larger land masses and then breaking apart into smaller, more numerous land masses. And so we start off with a single continent. It will want to eventually break up, so we will start having these rifts where we will be forming new crust, which will become oceanic crust. It will be that denser crust that will want to sit lower. Because it wants to sit lower, the water will collect there and it will eventually become an ocean. And so we will split our continent into multiple pieces. They will move apart. Eventually, once the continents have moved apart, it's no longer a rift. It is now a mid-ocean ridge. Those mid-ocean ridges will keep forming. Eventually, we will have to have subduction. Well, we will rather have subduction happening somewhere else because the Earth has to remain the same volume. So we will have subduction zones that will be consuming ocean floor. When we're consuming ocean floor, eventually we will consume the entire ocean. And so we can pull the mid-ocean ridge back into the mantle. As we're consuming ocean floor, we're pulling along whatever pieces of continent are on that same plate. And so as we are consuming the ocean floor, we're pulling the continents back together. And so eventually we will pull this continent back together and it will then be colliding into another piece of continent, and then those two continental pieces will merge up into a larger continent. And so we go through this cycle of having all the pieces break apart into many small land masses and then having them come together into fewer larger land masses. And this is the Wilson cycle of basically creating supercontinents and breaking up into smaller sections of fewer continents. So the thing that makes this happen are these different driving forces. So we have basal drive, which is the idea of we're riding along on the mantle convection. It kind of helps keep things moving. We have slab pull. Slab pull is the idea that slabs, the lithospheric plate rather, is more dense. We call it a slab. And because it's more dense, it has negative buoyancy, means it wants to sink. So it's going to pull down into the mantle. Um, Also, as it's moving down into the mantle, it's hitting higher pressures and different temperatures, so it's actually going to change minerals. The minerals will change and they can become more dense and then make it even heavier and want to sink more. We also have ridge push. So ridge push is this idea of we are upwelling materials at the ridges, and so we're going to have a high point, and so we're going to have material want to slide downhill. Also, as this process is happening, this lithospheric plate is cooling, so it's getting more dense, so it's wanting to pull down anyway. And then the final one is going to be retreat and rollback. So this is the idea of if you have two plates coming together, they're not always coming together at the same velocity, so you can have a basically a gap. You can have an uncompensated velocity, and so when that happens, one of them will either pull back or the other one will roll into the empty space. You can't have a void. So convergence rates can create a situation where the subducting plate will actually roll back, and so you can have that pulling more of the plate. The biggest ones on this are going to be slab pull is probably the biggest driving force, and then ridge push would be the second biggest. But slab pull is really what's driving this. You can think of the slab pull and the ridge push as being those large cells, that large convection cell within the mantle. So how fast is plate tectonics? Geologically, this actually happens pretty fast. So we're talking millimeters to centimeters per year. Are you going to be able to go out and look at a plate do this? No. But in some of these places, you could go out and take a GPS measurement from one year and then take the next year, and there's a difference. So we can use very sensitive GPS to measure these rates. So for example, these are all in millimeters. Like down here we have 127, so that's 12.7 centimeters. This is 5.3 centimeters. This is pretty significant. So this happens pretty fast geologically. So again, we can look at our plate velocities. In order to look at these, we have to put them into what's called a reference frame. So these red arrows are absolute plate motions, which means that's how fast the plate's actually moving. The black arrows are relative motions, so that's saying how fast one plate is moving in comparison to another plate. So we can see that, for example, here in South America, they are coming together. That's a convergent boundary. And so in order to study this, we have to put these things into what we call a reference frame. So a reference frame is how we describe the plate motion. So we either have relative reference frames where we're going to describe one plate compared to another, or we can have an absolute reference frame where we are comparing things to a quote fixed mantle, that we're saying the mantle is staying steady and we're moving all the plates on top of it. Typically to do that, we use what's called the hotspot reference frame. Unfortunately, hotspots aren't truly fixed, but they move in a predictable pattern. So what the heck is a hotspot? A hotspot is a volcano that doesn't really belong there. It's not on a plate boundary. Because remember I said the volcanoes outline plate boundaries? Well, sometimes they don't. So they're a volcano that's in the middle of a plate. It's not at a boundary. The best example of this is Hawaii. So this is going to form due to an upwelling of hot material from below. And so basically you've got this spot that's heated material coming up from below and the plate is moving over top of it. So we can use this to track plate motion because you've basically, assuming that spot doesn't move, you're assuming that hot spot doesn't move, and then the plate moves over it. The plate moving over it will produce volcanoes. Those volcanoes will be different ages, and so we can look at the age to figure out how fast the plate's moving, and we can look at the locations to determine if they've changed directions. So for example, Hawaii and the Emperor Seamounts. Seamounts are volcanoes that aren't above the seafloor. So they're not a volcanic island. It's a below sea volcano. We see in this chain that there's a bend about 43 million years ago, which tells us that the Pacific Ocean changed, or the Pacific Plate changed directions at that time. So this is what actually is happening, that we have our heated area that is rising up, and that's where the volcano is going to form. So in Hawaii, the big island is where the volcano is actively forming. That's where all the eruptions are. As the plate moves over this area, the volcanoes that we're forming are going to lose contact with that hot area. And so they will no longer grow and they will get older and older and older. Eventually, they will actually go back beneath the ocean floor and become seamounts because they're no longer actively growing, they're only being eroded. So we can see that starting to happen here. That's no longer actively growing and it's getting shorter because it's being actively eroded but not growing. And again, we basically are marking the motion of the plate with the location of the volcanoes, and we can figure out the timing of the plate by the different ages and how far away our older volcanoes are from the current volcano. So if we bring all of this back to Wegener, plate tectonics fits all of these pieces. So the the continents look like they fit together because they did used to be together. We see the same rocks across different continents because the continents used to be together, so those rocks were being formed across that boundary, or that you know there was no ocean there. They were forming on the same continent. We see the same animals because again there was no ocean there, so the animals and the plants were able to move freely between the different continents. We see evidence of past glaciations in regions that are currently tropical because those regions at one point were at the poles. We see evidence of tropical life forms in regions that are currently polar because at one point those polar regions were at the tropics. So everything fits together. And now we have the means of moving the continents. Wegener was right, the continents moved. He just didn't understand how they could have moved. So the continents as part of the plate moves, and so we have seen this repeated pattern of the continents moving apart and coming back together. And so all of his evidence was spot on. He was right. The continents used to be together, and his reconstruction of Pangaea was very accurate. The problem was, how did they move? So why is this important for... Okay, I stole this much of this presentation from my natural hazards class. Why is this important for natural hazards? Well, plate tectonics actually will tell us where hazards are likely to occur. The hazards maps outline our plates. For example, the Ring of Fire, which are the volcanoes around the Pacific Ocean. They are there because of plate tectonics. So many hazards occur on plate boundaries, things like earthquakes, volcanoes. We also see a lot of topography or elevation, the changes in land surface at those plate boundaries. So for example, mountains, so landslides. So much of our natural hazards are going to be connected to plate tectonics. In a bigger scheme of things, why does this matter for Earth science? Plate tectonics controls most of Earth's processes. This is kind of the overriding thing that controls the surface of our planet. So the plate boundaries shape our planet. They outline our planet. This is why our planet works. So large-scale plate tectonics is what makes our planet dynamic. It's what makes our planet work. And it's basically all of our, if you think back on it, everything we're going to talk about in this class is somewhat controlled by plate tectonics. So it's a very important key part to understanding our planet. So now I'm going to show the pre-lab video for this week, which is on plate tectonics.
Hi there students, this is Callan Bentley. Welcome back for another pre-lab video. This week in lab, it's all about plate tectonics. Plate tectonics, of course, is that unifying theory of modern geology that says the outermost rocky layer of our planet is broken into a series of pieces, and those pieces move relative to one another like giant slabs or plates. These plates can consist of continents, they can consist of the rock that floors the bottom of the ocean basins, or both. So like the North American plate, for instance, includes both continental lithosphere and oceanic lithosphere. The plates will have various kinds of interaction with one another. They can either be moving apart from one another, what we call a divergent boundary. They can be moving toward one another. That's called a convergent boundary. And they can be moving laterally, sideways, past each other. And that's called a transform boundary. So on this map, the divergent boundaries are shown in red, the convergent are shown in blue, and the transform are shown in green. Most earthquakes on Earth are associated with plate boundaries, about 95% of them. And some of those earthquakes are at the Earth's surface, in other words, they're shallow. And at other locations, we see a pattern of progressively deeper and deeper earthquakes going into Earth's interior. And these are known as subduction zones. So here on this cross-section, for instance, looking at the subduction zone at the Tonga Islands, the Tonga Trench, you see that there is a cluster of shallow earthquakes near the trench itself. There's another group of earthquakes that are of intermediate depth, not directly below the trench, nor laterally sideways relative to the shallow earthquakes, but instead at a greater depth. And then there are even deeper earthquakes beyond that. Basically, what this shows us is it's almost like an X-ray into Earth's interior, showing us where that subducted plate is going. As it interacts with the rock on its way down, it sticks and slips, and that generates earthquakes. So that's a classic example of a convergent plate boundary. Here's an example of a divergent plate boundary. If you look at the continental crust of the continents of South America and Africa, you'll find that both of them have a piece of really old crust called a craton near their middles. All right, the Congo craton and the Sao Francisco craton. This is the sort of evidence that Alfred Wegener looked at when he was deducing the idea of continental drift, that there were these sort of pictures that were only complete when you matched up the puzzle pieces. So you can probably infer by simple logic that if the Sao Francisco craton and the Congo craton are really part of the same craton, then we would expect that the age of that craton would be older than the breakup, that South America and Africa broke up sometime after that craton originally formed. In other words, it would be a way of figuring out the timing of the plate tectonic motions. Another way of doing that is using the pattern of reversals in Earth's magnetic field. This colorful looking diagram here is basically a time scale that's based on magnetic reversals, where each of the colored blocks refers to a period of time when the Earth's magnetic field was the same as it is today. So in other words, the north magnetic pole coincides with the north geographic pole. The periods of time when that was not true are colored here with sort of a neutral color. That's when the needle on a compass would have pointed towards the south geographic pole instead. Well, if we use that color coding to highlight these stripes of magnetized oceanic crust, we see an interesting pattern emerge. First off, you see that regardless of whether we're talking about the North Atlantic Ocean, the South Atlantic Ocean, or the Pacific Ocean, the pattern on the left side of these images is the same as the pattern on the right side of the images. In other words, they're mirror images of one another. So you could think about this as a tape recorder that's running in two directions at the same time, recording changes in the Earth's magnetic field. However, the tape is not running at the same speed everywhere. And one way you can convince yourself of this is by finding a distinctive marker. For instance, in this picture, we noted that we've got these different colored magnetic stripes, and 2 million years ago is basically where this green stripe begins. So if we go and we look at these images, we can say, all right, so that is 2 million years ago, that is 2 million years ago, that's 2 million years ago, that's 2 million years ago, that's 2 million years ago, and that's 2 million years ago. So we've got 6 locations where we know the exact age of the crust just for that one period of time. What we need to do now is say, all right, everything between that 2 million years ago and the center of the ridge today, which is 0 million years old, has been produced in 2 million years. So how much lateral extent of crust has been made in those 2 million years? The easiest way to do this is to put a piece of paper between those 2 points, take that piece of paper and line it up with the scale, and then basically read it off the scale. And here it looks like we've got about 37 kilometers worth of crust produced in one direction during that 2 million year span. So you've got 37 kilometers of crust produced in 2 million years of geologic time. Do the math, and you end up with 18.5 kilometers per million years. Another way of assessing the rate of plate motion is to look at hotspot volcanism. Hawaii, the U.S. state of Hawaii, the archipelago of Hawaii, is a classic example of hotspot volcanism, and it's part of a very long chain of islands that includes the Emperor seamounts going up towards the subduction zones in the northern part of the Pacific. The bottom line here is that the islands are of different ages. The youngest island is the Big Island of Hawaii, which is continuing to form today through eruptions of new lava. The oldest of the main islands is Kauai, which basically has lavas that vary in age between 3.8 and 5.6 million years old. All the other islands in between are of intermediate ages. So essentially, you can figure out how fast the Pacific plate is moving by going and picking 2 spots, like say Oahu and Maui, and figuring out the age of the different volcanoes there. Say Oahu's 3.3, Maui's 1.0, so there's 2.3 million years of geologic time that has passed between when Oahu was over the hotspot and when Maui was. Again, we're going to need to go ahead and measure the physical distance between them, use the scale, and basically that will allow us to calculate a rate. This rate is a vital quantity because it allows us then to figure out how old a given ocean basin is. If you know how quickly, say, the North Atlantic is opening, then you can measure the distance across the Atlantic from the edge of the North American continental shelf to the edge of the Northwest African continental shelf and divide it by that rate, and you can end up getting the age of the Atlantic Ocean. It's a pretty powerful thing to be able to do. Now that you are empowered with these new abilities, it's time to go and work on lab. Good luck!
All right, so that is plate tectonics, and hopefully you find it as interesting as I find it. I happen to love plate tectonics. So now we're going to, in the next few weeks, talk more about the actual physical Earth. This is the part that I really, really enjoy, and I'm hoping that I can show you how awesome the Earth is as well. So I will see you this week. Have a good one.